Thanks. So yeah, today I'll be talking about our work on automated conflict event coding using large language models. And so first of all, this project sits within a larger initiative called the Peace Science Infrastructure, which is a collaboration between PRIA, Uppsala University, Cypria, and the University of Oslo, specifically our Department of Informatics and also the Department of Political Science. And so the goal of the language technology group, which I represent, is to develop tools to automate the extraction of conflict events from text. And to do that, we're using large language models, as many of other presenters during this conference do. And so we also fine-tune it on curated data from UCDP. And let me start by framing the core challenge of such automation is that when we look at a news article, let's say this report from Gaza from July 2014, the traditional natural language processing approach would extract text spans directly from the document. So for example, you would get children as the victim, you would get yesterday as the date, and 4 as the death count. But this is, of course, not what conflict researchers actually need. And what we need is the abstractive coding, which is the expert level analysis that goes beyond what's literally written in the text. And so for the same article, a trained coder would identify the victim category as civilians, then infer the perpetrator as the state of Israel based on their contextual knowledge, and then convert yesterday to an exact calendar date, determine that 5 people died in total, including the mother. And so this is the gap that we're trying to bridge using large language models. So the gap between the simple extractive paradigm in the abstractive expert analysis. And as I'm sure all of you are aware, LLMs require large amounts of data for training. And in our case, we're lucky to have UCDP GED, the georeference dataset, as our data source. And so there, each conflict event is coded across 14 different fields that cover 4 main categories: the actors, the dates, the geographic location at multiple levels of granularity, and the detailed breakdown of casualties. And so this is a very rich structured output, and getting a model to produce all of this information is not a trivial task. And today I'm going to talk about one modeling experiment that we've done at LTG. And for our training setup, we applied several filters to the UCDP data by keeping only documents that describe a single event, filtering out very short ones, and truncating the long ones. And in order to train a model, you would need several data splits. So you would split your data into the training, validation, and test sets. And our splits follow a temporal logic. So this is important because then when we train the model and test it on the test set, we try to test if the model can genuinely generalize to unseen future events rather than those events that it has encountered during training. And I am going to present one particular model, which is a FLAN T5. It's a large language model, which is a encoder-decoder architecture with a 780 million parameters, which was pre-trained on different NLP tasks from text summarization to classification and so on. And so what the model does is that it takes a text document as an input and produces a structured event representation in the UCDP format as an output. And we select the best model during training based on the mean string accuracy across those 14 fields that the UCDP has. And so before I show the quantitative results of this modeling experiment, I would like you to invite to try the model yourselves. So we have a demo running on Hugging Face basis, which is the left QR code, and also the address that is on the screen. You can there paste in any conflict event into the model and see what it extracts. And I am going to do that live here with you and hope that it works. So here, as an example, we have an event, which is the news article from May 2014 about the gun battle in Pakistani tribal area near Lanti Kotal. And so what we see here is that the model has just extracted this representation of the event in UCDP format, and it correctly assigned site A to the government of Pakistan, side B as TTP, although it's not directly present in the text. Then it has resolved the late yesterday to the correct calendar date. And then it counted the total number of deaths correctly. So we have in the article 8 militants and 2 soldiers for the total number of 8 deaths. And also the geographical position, it has also assigned correctly the country and the different administrative regions up to the finest granular distinction here. And so what we can also see in this case that although it extracted the correct event from the text, it ignored everything else that has been given. So for example, there is a description of another event in the text, which was not taken into account. And this is to be expected because so far we're training the model on single events. And so it is expected to just extract a single event from the text. But let's have a look at another event. I will just copy and paste something here quickly. So this one is from Russia, and it is about North Korean soldiers being killed in the Kursk region of Russia. So the model takes a couple of seconds to run inference and extract the representation. And here we can see that it has incorrectly assigned North Korea as side A. So in this case, the UCTP would note that the accident involved North Korea as the secondary warring party, whereas side A should definitely have been Russia in the Russian-Ukrainian conflict. And it also undercounted the number of deaths. So here it presents 8, although 13 were given in the news article. So maybe in this case, it is getting confused by the 8th regiment in the text. So far, although the model does well in some cases, there are definitely other cases where it fails, which again underscores the importance of human supervision. And so going back to the results, so those were the 2 different events that I have just run together with you. When we looked at the 10,000 news articles that we tested our model on, we can see that the results overall are promising. And so the model extracts the correct representations from the text 80% of the time. And so group by category actor identification is quite good, achieves 90% accuracy, followed by death and then location. And location is the most challenging part. So the country level location, so this root name location is quite easy with 96%, but then as we go finer to the exact specific location where the event has happened, it becomes harder for the model. And this is actually not surprising in a way because this requires fine-grained geographic knowledge, and also those finer-grained location names are oftentimes actually missing from the text from the training data. So overall, the results are promising, but they are not without limitations. And I'm sure many of these limitations have been mentioned several times during the conference, but the main one is that the model will inherit all of the data assumptions and biases that we have in the training data, right? So all of the specific actor names, conflict times, or the geographical coverage, whatever you have in your training data, you can expect to see in the model. And it is bound to be sensitive to our methodological choices of how we code data, for example. And then as a generative model, it can produce plausible sounding but factually incorrect values. And it is often the case with those open domains, such as actor names and location names, the finer grained one. And so far, this model that I just shared, which is openly available, is only trained to extract one conflict event from one document. So it will not generalize well to documents that have 0 or more conflict events. But those are the directions for future research. And here at LTG, we are actively working to train more models and make them better at conflict event extraction. So thank you.